So if your cobalt is at the center, we have another case where we have an octahedron. In this case, we're going to put 4 NH3s around this. And we're going to have 2 chlorides on here. So this particular complex ion has a +1 charge. One of the things here is, can we, and if I made this particular complex, this one right here would be violet. And in terms of the other cases that we looked at, in this particular case, we have 2 chlorines here that are directly bound to that transition metal center. In this particular case, the chlorines are right next to each other. Or we can say in the coordination environment, they are adjacent to each other. The question is, what happens if we drew this complex a little bit differently? So instead of putting the chlorines right next to each other, what happens if I put them 180 degrees away from each other? We still have our 4 ammonias over here. And we have a +1 charge for this complex ion. In this case, we have our chlorines 180 degrees away from each other in this particular octahedron. When we do that, this particular complex is going to be green. And what this led the chemists of the time to determine was that, hey, it matters how we coordinate these ligands around the transition metal center. And in certain instances, and it's really going to depend on how many of these ligands that we have. For example, if we went back and looked to the first complex ion that we analyzed, we have a cobalt with 6 different ammonias attached to it. In terms of like statistics or looking at what could be going on in this particular complex, is there any other ways that we can arrange those ammonias around that cobalt? There's 6 of the same exact ligand. So there's really only one way to place all 6 of those ligands around this cobalt center. And that's why there's only one color for this. In terms of the other example that we looked at, we have cobalt, and if we put 5 ammonias around here, and 1 chlorine, we only have this 1 chlorine here. And what I kind of touched on earlier is that you need to be able to visualize these things in 3 dimensions. And in reality, when you have a molecule in solution, it's rotating around. So the question is this particular complex right here, if we drew it differently and kind of rotated it, because what happens if this chlorine right here and this ammonia switch places? Is that going to change anything in the molecule? There's really nothing that changes in terms of bonding. It's just like I'm rotating it, instead of drawing it like this, I'm drawing it like this. Nothing really changed here. But with these other complexes, by putting the 2 chlorines adjacent to each other versus on the other side of the coordination sphere, we're going to get different colors, and we have to come up with a different nomenclature system for these different types of complexes. The term that was used was called an isomer. And the term isomer refers to compounds with the same overall composition, but different structures. So if two particular complexes have the same formula but a different structure, we refer to them as isomers. In this particular case, if you have two ligands that occupy adjacent vertices, we refer to this isomer as cis. And if two ligands occupy opposite vertices, we refer to those as trans. And we're going to go over all the different types of isomers later next week sometime. But this is going to be a great way to kind of give a reason for why particular substances might have a different color. So what Alfred Werner then did was he took all of this information and he kind of put it all together and kind of came up with a theory. Okay? So what he said in his theory was this. So Werner saw that when there are fewer than 6 ligands around CO3 plus, Cl minus would form a strong bond to the cobalt 3 plus, making the coordination number equal to 6. And that's going to give us an octahedral geometry. So there's a couple things that I've introduced here, and one of them was coordination number. And essentially, what Werner did was he came up with two types of vocab words based on all these theories here. The first one is coordination sphere. And the coordination sphere is the central atom and the ligands directly bound to it. There's also a term called coordination number. And this term is the number of ligands directly connected to the transition metal center. And typically the most common one that we'll use is coordination number. So we need to determine, various coordination numbers of these transition metal complexes. And in terms of that coordination sphere, which is the number of these atoms that are directly bound to the transition metal center, we can kind of look at these complexes, and as we showed before, we put them in brackets. So if we had CO, NH3, 4, Cl2 inside of the brackets with the Cl on the outside of the brackets, we refer to this Cl right here only as a counter ion. So if I ask for the coordination number of the cobalt, one of the things that we definitely have to consider is we consider only the ligands inside the brackets. Okay? So if we're analyzing the coordination number, in this case, we just look at everything that's inside these brackets here. So the coordination number of the cobalt, in this case, is going to be 6. It's coordinated to 4 ammonias plus 2 Cl minuses. And when you look at the coordination number, especially for these transition metal complexes, if we have a coordination number of 6, we're going to have an octahedral geometry. You should get one of the common coordination numbers from the Vesper shapes back in Chapter 8 and Chapter 9. If you get a number like 11 for a coordination number, that's probably something's going on here. So one of the most common mistakes that students can make in these particular examples is to not, or to include the counter ion. Remember, the counter ion makes these particular complexes salts. If I take a salt and dissolve it into water, it's going to give me a cation and an anion. When I refer to the coordination number of a complex ion, we are only referring to the particular cation. So that's going to be everything here inside of these brackets. So that counter ion is not directly bound to the transition metal center, and this is going to dictate a lot of the properties of these salts when we add them together. So make sure that when you're looking at these complexes, you don't consider the counter ion to be directly bound to that transition metal. Okay? Another thing that we can ask here is, typically when I give you a complex like this, I'll ask you for 3 things. The first thing is the coordination number of the transition metal center. We answered that, that was 6. Second thing would be the geometry. In this case, it would be an octahedron. The third thing is we also ask for the oxidation state of the transition metal center. And this is where the charges of our common cations and anions come back into play. Because in this case, we know that ammonia is neutral. So the NH3 ligand is not going to have any charge associated with it. In this case, the chloride has a -1 charge, and there's 2 of them. And this chloride right here has a -1 charge, and there's only 1 of them. We also know that when a salt is formed, it's got to be neutral. So in this particular case, we have our negative end, or our negative charge, is going to be -1 plus 2 times -1, or -3. So that means to give an overall charge of 0, the transition metal must be +3. So in this particular case, the oxidation state of our transition metal is going to be +3. And with that, you need to add up all the charges of all of the ions that we have that are attached to that. Whenever we form salts, those salts give us a neutral compound. And it goes back to the same principles that we looked at with other complexes, where, example, for like barium sulfate, it's going to be BaSO4. Barium chloride, BaCl2. Okay? With these transition metals, one of the things is that we can have varying oxidation states. So it's going to depend on how many ligands you have around that to determine what that oxidation state is. And we're going to pick up with oxidation states, coordination numbers, and geometries on Monday.